Okay, so in our next unit, we're going to talk about how to recognize functions by looking at tables. And again, like you don't necessarily need to have a table to do this because you could always look at a graph and make a table using the values in the graph. But what this will do is it'll help us determine what kind of function we're working with. And then from there, we can figure out the equation and just learn a lot more about it. So the first ones we're going to look at is linear functions. So, and this is something we've seen before. So, as you can see, like every time x increases here, plus 2 on x, plus 3 on y, plus 2x, plus 3y, plus 2x, plus 3y. So what's happening, we can see it with the table values. We're adding 2 to the x value, and every time we add 2 to the x value, we're adding 3 to the y value. And this is the same for all of these. 1, 3, 5, 7, 9, 4, 7, 10, 13, 16. It's just adding 3. So this is where the slope shows up, right? Like this is your rise right here, and this is your run. Let me fix that arrow. There we go. All right. And so what we're seeing here in the table is we're seeing an add pattern. And to clarify what that means is we're adding on the left side of the table and we're adding on the right side of the table. Pretty straightforward, but it's a signifier that like, oh, when x increases at a constant rate, so does y. Y increases at a constant rate too. That means we're going to have a linear function, meaning it's just going to be a line. Now let's look at exponential functions. So um, it's harder to get a bunch of different values on the graph just because exponential functions grow so fast. But what we're seeing here is that we're going from 1 to 3, and then this is going, at 1 it was at 15, now it's at 135, and then, you know, if it fit on here, it would go all the way up to 1215. Um, so a way you can figure this out, and this might be a good way to test to see what's happening, if it's adding, if it's multiplying, whatever, we could divide 135 divided by 15, and that's going to equal 9. Well, then what's this next number? 1215 divided by 135. I'm just dividing like this number by the one before it and this number by the one before it. That also equals 9. So what's happening here is we're doing times 9 each time. These are all increasing by a factor, a multiplication factor of 9. So this is just adding 2, right? 1, 3, 5, 7. So exponential functions follow an add multiply pattern. And that just means it adds on the left and it multiplies on the right. So that's something, this is kind of how you would test that out. You can divide the number before it by, you divide that number by the number before it. You could test that out here too, and it wouldn't work, but you could also, you know, you can see, oh, it's adding by a constant rate. So there, you kind of test both to see if you're not quite sure. So power functions, this would be like, I'll just write down the equation for this graph. This is, the book messed this up. This should be an H because it's an H on the graph. So this is h of x equals 5 times x cubed. So it's a power function. It's a function, you know, it's like higher than a quadratic. Well, quadratic would apply as well, but there's also another rule for quadratics that's a little easier. But for higher power functions, you can use this rule. So what we see when we're looking at the graph is x is increasing from 3 to 6 here, And when it goes from 3 to 6, it goes from 135 to 180. And then from 6 to 12, it goes from 1080, goes from 1080 to 8640. So there's clearly like some huge growth here. So the trick with power functions, and I think just deriving this first might be a little confusing. So what I'll show you is this is from 3 to 6. Well, that's plus 3, but it's also, so this is 3, 6, 9, 12. You're adding 3 in this column. There's not as much of a pattern there, but if we do the multiplication, so it's times 2, 3 to 6 times 2, and then from 6 to 12. So we're going to ignore 9 and this whole, that whole point, and we're going to go 3 to 6, we're multiplying by 2, and then 6 to 12 is also times 2. So what's happening here is, and you can divide 1080 by 135. Obviously, these aren't adding because the rates are changing much more drastically. But 1080 over 135, well, you can even see it here. It's going to be times 8. And then this one, 8640 divided by 1080 is also times 8. So we're multiplying on the left side by a factor of 2, and on the right side we're multiplying by a factor of 8. And it actually works out that it doesn't even have to just be 2, right? Like we see 3 and 9 in this table. Three, 6, 9, 12, 135, 1080, 36, 45, 8640. So if we wanted to say, well, this is times 3, 3 to 9, that's times 3. Maybe I'll even use green. Right here, that's times 3. So what is this? Well, this is going to be 36 to 45 divided by 135. That is times 27. And so I'm noticing a pattern here because I know since we just did our exponential unit, how 2 and 8 are connected. Remember, 8 equals 2 to the third. And I also remember 27 and 3 are connected. 27 equals 3 to the third. So there's a relationship here. We can kind of, it'll tell us a lot about the equation. Like just if we only had these tables, we could see this relationship and say, oh, this is a cubic function. It's being cubed. And I'll show you where that comes from real quick. This is 5 times x cubed. Well, let's say we're going to plug in 3. So h of 3 equals 5 times 3 cubed. And that gives us 135. Now let's look at h of 6. H of 6 equals 5 times 6 cubed. Well, 5 times 6 cubed, remember we just did a lot of this in our exponential units. 6 is the same as 3 times 2. And then remember our power of a product property says that we distribute this 3 to both the 3 and the 2. So this equals 5 times 3 cubed times 2 cubed. And if you look at this, 5 times 3 cubed, that's actually equal to h of 3, right? So we can swap that out and say, well, h of 6 equals this, then it also equals h of 3 times 2 cubed, which is 8, right? So it's equals 8 times h of 3. And so if we looked at how we looked at here, where multiples of 3, like if I did h of 9, I would have been able to factor out 3 cubed. And so each time I'd be multiplying by 3 cubed. So that's a little trick for figuring out whether it's, cubic or x to the 4th or 5th or 6th. It helps you figure that out. So what we call this, the power function follows a multiply pattern. Go back to red. Because we're multiplying on the left side of the function and we're multiplying on the right side of the function. Oh, sorry, this pattern. I can't talk and write at the same time. All right, so the last one we're going to look at is quadratic functions. And this one's definitely got the funkiest name. And it's got a little extra step on it. But so what we're seeing here is 1, 3, 5, 7, 9. So again, we're back to just adding plus 2, plus 2, plus 2, plus 2. You can't multiply any of these together to get the next one. It's clearly just plus 2 each time. And then, well, I could like 19 divided by 5. That's going to give me a gross number. 57 divided by 19. That's not going to give me the same number. You can try it out if you want, but those are. It's not going to. They're not being multiplied at a similar rate. Adding. I mean, this is what 15 to 5. You're like minus 10. 5 to 19. You're plus 14. 19 to 57 would be. Plus 38. And then I guess this one would be plus 62. So that's not really like a good adding pattern either. But if you look closer at those numbers on the right, negative 10 to 14, there's a difference there. You're adding 24. 14 to 38, you're also adding 24. 38 to 62, that's also plus 24. So you're adding a constant number to the difference. So this is called a constant second difference pattern. So this right here is the second difference. This would be the difference, right? The difference between 5 and 15 is negative 10. The difference between 19 and 5 is 14. This is the second difference is what we're calling this. But it's the difference between the differences. And it's constant. So that will tell us it's a quadratic function. So that's something you can look for there. So that's it for this video.